Hello, my name is Dimitrije Stefanovic. I am a researcher at BioSense Institute from University of Novi Sad, Serbia. I will present you a joint work with my BioSense colleagues Vladan Filipovic, Nina Pajevic, Zeljana Grbovic, Nemanja Djuric, and Marko. In this paper, we propose a new dataset for bush detection in blueberry orchards and present a baseline results using YOLO V5 models. Bush detection occurs as a problem within Horizon 2020 FlexiGrobot project, funded by European Commission, where the main goal is the application of unmanned ground and aerial vehicles in agriculture. In our pilot, we developed UGV for blueberry orchard monitoring, where detecting blueberry bushes is a key component of our UGV guidance system. Also, in a lot of forestry and different agricultural applications, bush detection could provide significant information in different research areas. As far as we know, bush detection is an unexplored area, and there is no data sets of this kind. In the most cases where the tree detection is being studied, authors are detecting trunks, but there are no bush-like examples such as blueberries. Therefore, we present this new data set, which was collected in blueberry orchard located in Babe, central Serbia, and we used our robot platform named Gari, equipped with OAK-D camera to capture 2000 RGB images. Dataset is publicly available on Zenodo, and it can be accessed through QR code in this slide. Images were collected from UGV perspective at the height of 0.5 meters. The data comprise 20 image sequences of variable length captured in 3 dates, and some of the statistics are shown in the top right charts. The camera was mostly directed from the row center towards the plants, although there are sequences where the camera is rotated to look down the rows, as can be seen in the figures below. Within the dataset, there are 2 types of objects that are important for guidance, bushes and poles. The bush label corresponds to the base of the blueberry bush, and it is important, for example, for UGV alignment and micro-positioning in the orchard, while the pole label corresponds to the hail netting poles and similar obstructing objects such as lampposts or wooden legs of bumblebee hives. And distinguishing these poles is important to prevent equipment damage in operations such as soil sampling or pruning. Dataset introduced numerous real-life variabilities such as bush shape, where each bush has unique features such as branch ordering or number of branches, pole types, for example, anti-hail net poles, bumblebee hives, lampposts, etc. Also, there are different levels of contrast and shadows, occlusions such as branches, leaves, weeds, and so on. Regarding the limitations, dataset is captured in a single orchard during daylight, and most of the images are captured during season. There is no images captured in winter conditions or during the night. For this particular problem, labeling was not as simple as for objects such as cars, cats, dogs, or any other compact objects. First, 400 images that captured the data variability, such as various types of bushes and poles, were handpicked and manually labeled. For bushes, plant base was the region of interest that we annotated using bounding boxes, where we tried to catch the information about triangular shape of bushes and its contact with the ground. For poles, the task was much easier as they are simpler objects. These images were divided into 10 subsets, and each was labeled by a different annotator. An initial YOLO V5S model was trained using the manually labeled data and further run on remaining 1600 images. Annotations obtained in such a manner were visually inspected, manually corrected, and added or removed when necessary. We trained YOLO V5 models for detecting our objects of interest in 3 complexity levels, nano, small, and medium. Training validation test splitting is done based on sequences to prevent data leakage, and the ratio of splitting was 75, 10, 15%. Regarding the augmentation, horizontal flipping was used, as well as HSV scaling and mosaicing. In the figures below, there are several examples of these augmentations. Quantitative results showed that trained models achieved promising performances during evaluation on the considered task, thus setting a good basis for further work on improving the performance of the task of blueberry bush detection. As for the qualitative results, in this kind of analysis, results must be analyzed directly, and besides labeled the instances that were detected correctly, a large number of objects of interest were successfully detected, even though they were not labeled by the annotators, as can be seen in the examples below. We obtained promising model performances in most cases, even when shadows, weeds, and occlusions were included. When having trouble with ambiguity notations, faraway objects, and image rotations, and we got good generalization abilities with unseen objects. Detection speed, suitable for real-time applications, represents one of the most important characteristics of the evaluated models. In conclusion, we proposed new dataset for bush detection task. The YOLO-V5 models achieved promising metrics and thus setting a good basis for further work. Future work should include dataset improvement by adding more images, more augmentations, and further result analysis. Thank you for your attention.